those. It's funny. They're just sitting back.
Is there a clock in this one?
Wow.
It's
90 seconds. All right.
24. So, yeah, that's it's about time, and they will continue this first talk from yesterday on Operation K-theory.
Okay, so just quickly say some things that I did last time, or the ideas that I introduced last time. So for so X, a variety over an algebraically closed field, and I guess I'm going to let T be a torus acting on X. So there's the equivariant K theory of coherent sheaves on X, and this acts like a homology type theory in the sense that it's covariant for at least for proper maps of varieties. And what I started introducing was well, I guess so. There is a natural geometric cohomology theory. So this is K theory of vector bundles. And really, I mean perfect complexes. But so basically, K theory of vector bundles. So this is geometric, but hard to work with, and so instead, I started looking at operational K theory. So operational equivariant K theory. And what this is it's a collection of operators. So these are elements are operators on the homology of anything that maps into X. So any Y that maps into X, you get you just define a certain kind of compatible collection of operators. And this thing this operational K theory satisfies a universality property, which I'll just write in words. So any functor which agrees with with ordinary K theory for smooth varieties, admits a canonical natural transformation to op K. So this is sort of the most useful way of thinking of it, and lets you kind of build things up from facts about smooth varieties. Right. So one reason why, well, an example, I guess, of why ordinary K theory of vector bundles is hard is the following. So I mentioned this last time, that these things can happen, but let me just give you a concrete example. So K theory is not homotopy invariant. And so if I just take X to be a cubic cusp, or a cuspidal cubic in the plane, then one can compute, basically for curves, K theory is easy to compute. It's just is essentially the same as knowing the Picard group. And so so that's the case. But on the other hand, so you have a pullback map to X cross A1, and one can use a sort of Meyer-Vietoris argument to compute that this contains the integers plus a polynomial ring, so it's certainly much larger. So it's not homotopy invariant. Okay, so the reason that I brought that up again is because I want to mention another version, another kind of variation on K theory that sits between regular K theory of vector bundles and this operational K theory that I described last time. So this is called homotopy K theory. And it was invented by Weibel. And it's essentially homotopy invariant by design. So KH of X is a ring. It's homotopy invariant. And it's sort of the smallest, in some sense, the way you should think about it is it's the smallest homotopy invariant functor that K maps to, that ordinary K theory of vector bundles maps to. The price is that it's a little bit somehow non-intuitive, because you can be non-zero in negative degrees. So maybe, okay, so it's not, I'm not trying to say that it's non-zero in every negative degree, but maybe non-zero. And it often is for singular varieties. Oh, yeah, thank you. Okay. So that won't explicitly play a role in anything that I have to say. But it does play a role in computations. Oh, and so one thing that is true about this, so in the sense, so part of the sense in which this is kind of a homotopization of the functor K is that at least when K theory, if you restrict to some category where K theory is homotopy invariant, like smooth varieties, then this becomes an isomorphism. So in particular, just at K0 is an isomorphism when X is smooth. And so it might be an interesting project for someone out there in the world to develop a equivariant version of this, but Weibel did not. And this is sort of well outside of my range of expertise. So everything that I say that involves homotopy K-theory, well, okay, it's equivariant for the trivial torus. So we're just forgetting T here. But in particular, because this is a functor that agrees with smooth schemes, there's definitely a transformation for any scheme X, for any variety X, by this universality property. Okay, so I'm going to write up a big diagram of just kind of summarizing the K-theories that we have so far. So there's what I'll call K-naive. So this really is the Grothendieck group of vector bundles, which may not be the same thing as the Grothendieck group of perfect complexes on varieties that can't be embedded in smooth schemes. But certainly there's a map. You can take a vector bundle to a perfect complex. And then there's this homotopy K-theory. And now I really wish I'd started this someplace else. I can leave a little bit more room. Okay, then there's operational K-theory. And then finally, there's this homology K-theory of coherent sheaves. And these are all isomorphisms when X is smooth. And just to mention one other thing, so the homotopy invariant part, these guys are homotopy invariant. And somehow the sort of more geometric things are maybe these. So these are kind of more geometric. Well, yeah, I don't have a precise meaning for that, so let me not say that. So that's the kind of zoo of K-theories that we have. Right. So I'm going to leave that up there and I'll come back to this in just a moment. So I want to I promised a couple applications. I'll have two in some sense. The first one I want to say, the first one I want to tell you about is the following. So there's this class of T linear varieties. And without getting into the details of what they are exactly, so these are defined by Totaro. And they're basically varieties X with, so I'll put this in parentheses, with a T equivariant stratification into affine spaces and certain open subsets of affine spaces. So let me just say in words what this means. So affine space is linear, and if you have a linear variety and you can embed it in affine space, then the complement of that is linear. And any variety that has a decomposition into locally closed subsets, each of which is linear, is also linear. And so this sort of gives you an inductive way of characterizing what these varieties are. But so it definitely includes anything that has kind of an affine cell decomposition. So, and more generally, it includes so like Schubert varieties, toric varieties, and much more generally so spherical varieties. So that's kind of the purview of this category of varieties. And so I guess this is a theorem with Sam. So what we showed is that if X is a complete linear variety, then the operational K-theory, and I can say equivariant, is just the dual of, so I guess this linear dual of the K-theory of coherent sheaves. And what is the map? The map takes an operator to, well, remember, so an operator operates on K-theory for every map of a variety into X. In particular, just take X itself. So you can operate on this. Okay, so I need to tell you what this homomorphism does. So it takes a class alpha in here, and first you operate by your given operator on alpha, and then you just take away their characteristic. So that's just proper push forward to a point. So that's what this is. And in particularly, so if you take T to be just the trivial torus, this just says that op K is just the linear dual. So in particular, for such varieties, for such varieties, one can also prove that the stratification gives you a generating set for the K-theory of coherent sheaves. Take the structure sheaves of the strata, and that generates K-theory of coherent sheaves. So this is finitely generated, a finitely generated abelian group, and therefore its dual is as well. In contrast, I guess, to this picture here. So this is also kind of clearly a linear variety if you just stratify it by the point and the complement of the point. And here you've got a copy of the field inside, so it's not finitely generated. Okay, so this tells you that for such varieties, this is some kind of finite thing. And it also tells you that if, for the purposes of computing Euler characteristics, which is something that you might want to do with K-theory, is, from a numerical point of view, that this captures all of the sort of numerical data of K-theory. Sorry?
It's just a map, or?
Oh, no. Oh, my God. Yeah. That's the statement. So this map exists no matter what, and the statement of the theorem is that it's an isomorphism. Yeah, okay, thank you. Yeah. So the map always exists, of course, for complete varieties. Okay, so now, let me, just to be careful, let me assume from now on for the rest of the talk that the characteristic is equal to 0, although some interesting things that I've learned from Zinovi and Brian just this morning basically may let us relax this. But since we haven't worked through the details, I don't want to. So there's a theorem by Cortinius, Hasemeyer. Okay, I'm sorry about my handwriting. That's because I forgot the order of his Hasemeyer, Walker, and Weibel from 2009. And what they proved is that for any a toric variety. So remember, a toric variety depends on a fan in some vector space. So for any toric variety, I'll just call this X. The natural map from K-theory of perfect complexes to Weibel's homotopy K-theory is a split surjection. So at this point, I should say that the distinction between this is vector bundles, and this is perfect complexes. And okay, so I haven't said it. I mean, this looks like a technical distinction, and indeed it is. But a basic question that I mentioned last time is, can you even find a non-trivial vector bundle? And toric varieties, as combinatorial as they are already cases where we don't know this to be true in general, even for fairly concrete. Yeah, so this is an isomorphism if, say, X is quasi-projective. Then you don't need to worry about the difference at all. But this is just a true statement. If you take this to be the perfect complex one, this is true regardless. And so what we were able to do is, so what we were able to prove was that for any three-dimensional, well, I guess, so I guess in the above situation, if the dimension of X is less than 3, or is at most 3, then then this map is surjective. And so as a corollary, for such X, oh, yeah, so let me write the corollary on another board. So the corollary for complete toric threefolds, K-theory surjects onto the linear dual of K-theory of coherent sheaves, and since this is this is surjective. So this is non-trivial. There's lots of coherent sheaves on such a on such a variety, and hence so it's non-trivial in a precise sense. Its rank is at least the rank of this, which you can compute. So when we prove this, so there's two things to say. One is this maybe can be taken as evidence that vector bundles should exist for such varieties, although it does not logically say anything about that. Yeah, and so that's kind of how we thought of it. And when we proved it, nothing more was known, but a theorem by Marcus Perling and Stefan Schwer. This is just last July. So any toric threefold has a non-trivial rank 3 bundles. Rank 3 vector bundles. And you can make their churn numbers as high as you want. So this is somehow sharp because I think so Sam Payne had found an example of a toric threefold that had no rank 2 bundles and no line bundles. So. Oh, yeah. Yeah, thank you. Yeah. Toric threefold. So in fact, this is also true. And the funny thing is that our methods both really stop at dimension 3. And there's something difficult that happens after that we don't know. So, yeah, so it would be interesting to see either examples or counterexamples to this in dimension 4. Okay. Okay, so I want to give one more. So the next application that I'll give is sort of a in the realm of counterexamples, but in order to get there, I need to develop a little bit more theory about Riemann rock. Okay, so the original context so I mentioned this last time. A little bit. So this is the sort of Fulton-McPherson machinery of bivariant theories. And so what these are is this was kind of a framework for analyzing and unifying Riemann rock theorems for including singular varieties in the story of Riemann rock theorems. But quite often, so the general Riemann rock framework involves some transition between K-theory and cohomology, or maybe K-theory of coherent sheaves and Chow homology. And their idea was to kind of unify both of them. So without saying without getting into too many details, I'll just say what they do. So a bivariant theory basically associates some kind of group. So a group associated to each morphism in a category. And together with some compatibilities. And operations like pullback, product, push forward, etc. But it includes, the reason that's called bivariant is it includes a covariant part. So this is just defined to be what you get by applying the theory to the map to a point. And a contravariant part. Which is what you get by applying it to just the identity morphism. And what they were most interested in was so their replacement, their abstraction of Riemann rock was called they called it a Grothendieck transformation. And this is just basically a natural transformation of functors from one bivariant theory to another, kind of satisfying, that commutes with all of the operations that each one gives you. So in particular, it's going to include some transformation from the homology, some Riemann-Roch homology theorem, and it's also going to include some Riemann-Roch cohomology theorem. And it includes actually strictly more than that as well. So I just wanted to mention that to kind of put in context what I'm about to say next. So one of the things that they proved was there's a Grothendieck transformation from a certain algebraic K theory. So these are F-perfect complexes. That's the to operational Chow theory, and this is kind of why they defined operational Chow theory to begin with, as the kind of the receiver for the Riemann-Roch theorem for in the context that they set it up. And so I said, so this is defined just kind of like it was like a. So I told you what the contravariant part was about of this last time, but this is only a little bit more general. These are operators. So this operational bivariant theory, it gives you an operator from Chow homology of a variety to a different Chow homology of a variety, one for each square, where y prime maps into y. Here's your given f, and then you just form the fiber square. And so this is a direct generalization of the case when this is an identity, because then you just have one map, and you would get an endomorphism. Instead of that, you should think of this as kind of a refined pullback. So these are pullback, kind of refined pullback. So that's what the. Oh, and I guess this is they did this for x and y, so quasi-projective. So, and these are all defined in the category of quasi-projective varieties or embeddable varieties. Okay, and so I guess I need to set something up. So I want to, before I write this theorem, I want to give you an equivariant analog of all of this. And in order to do that, I need to kind of recall. So the K theory of a point, that's just vector bundles, equivariant vector bundles on a point, that's just representations of the torus. And so that's, if you choose a basis, it's nice to think of that as Laurent polynomials in a certain basis. So this is for the torus, n-dimensional torus. And similarly, I guess I didn't say this explicitly last time, but the equivariant Chow cohomology of a point is just the polynomials, it's canonically polynomials in characters, and so this is just a polynomial ring that I've chosen a basis in characters. And so there's a canonical map from equivariant K-theory of a point to non-equivariant K-theory of a point, which is just Z, and that just kills all these variables. So there's and there's a kernel. And it's just generated by setting all of the UIs equal to 1. Okay. So now for any R module, R of T module, just thinking of this as a ring. M is not a good letter for a module. F. So I'm just going to denote F to F hat completion for completion along this ideal. And also, so this is just notation. A hat. So, right. Chow cohomology is a graded ring. So there's this, and a hat will be just the completion of that graded ring along the ideal of positive degree elements. But that's the same thing as just taking the product in this case. So this is graded completion. Well, that's not the right thing to say. It's the completion of a graded ring. Okay, so the theorem is that this is with Richard Gonzalez also. So there's a there's a Riemann-Roch transformation, or Grothendieck transformation. I'm going to also use subscripts to mean tensor with Q. And in particular, just taking the covariant part, the contravariant parts, there are maps of rings. Including an isomorphism between completed operational K-theory and completed Chow cohomology. So there are some. So the most complicated part in doing this is really just setting it up. I'll just make a quick comment on the proof. The proof is mostly formal, and just using the fact that so these operational theories are built out of kind of you're given a homology theory, a covariant homology theory that's in this case K theory of coherent sheaves, and you build it out of that. And given that we have a theorem by Edidin and Graham. And they tell you that just at the level of Oh, yeah, I should have said, in all of these cases, subscript means tensor with Q. So, did I do it there? Yeah, oh, yeah, I should do it there. Thank you. Yeah. So there's a few subtleties, but nothing too deep. Yeah. So let me. I want to mention before applying this. I'll apply this in just a moment. I want to mention an example of singular Riemann rock. So I had this picture of a toric variety up on the board last time, and I'll do a slightly different one. So P112. So this is a weighted projective plane. So this is a toric variety for a fan delta, which I'll draw. So it's almost the same as P2, except so P2 would be the case where this ray goes through -1, -1, and this one I've just moved the ray over a little bit. And that makes, so a toric variety corresponds to a collection of cones, and each maximal cone corresponds to a torus fixed point. And the thing that happened here, so this point, so the T fixed point, so if I call this cone sigma, so P sub sigma, this is a singular point. Actually, yeah, leave that. So call it sigma. So this is like a projective. I mean, it's an orbifold and it has a mildly singular point. The theorem that I showed last time said that op k. Oh no, there's something I always forget, whether there's a difference between this and the, yeah. So it's one or the other, and I'm sorry. So there's only one singular point in this variety, and it's just this one. So okay. Definitely for this fan, only this point is singular. Okay. So this guy, this operational K theory gets identified with piecewise exponential functions on the fan. And so let me write down for you a piecewise exponential function on this fan just for fun. Yeah, that's okay. And so this ray here is where U2 equals 2U1. So keeping that in mind, you should be able to check that these do glue together to agree along the overlaps. So what's the map to operational Chow cohomology? Well, Sam Payne's theorem was that this gets identified with the ordinary without the completion. This gets identified with piecewise polynomial functions in the fan, and then you just complete it. And the map is just take just expand these in power series. So there's nothing really mysterious at all going on. It's the easiest thing that you could do. So just expand in power series. So somehow from this point of view, Riemann-Roch is really quite easy. Okay. Okay, so let me ask a question and answer it. So the basic question is, how much does equivariant K-theory say about ordinary K-theory? So for example, so is this restriction? So certainly there's a map, right? This just takes a vector bundle and you just forget the T action. Just a vector bundle. And so if X is smooth, then the answer is yes. And the way that goes is there's this Poincare kind of duality which says that equivariant K-theory of vector bundles is the same as equivariant K-theory of coherent sheaves. And then this map is surjective. And the best reference I know for that is Mercuriev's paper. Of course, he proves it for much more general groups than just split tori. But, and then this is, again, by the same duality isomorphic decay. So this is surjective. But the answer is, so not in general, e.g. For a projective toric threefold, which I will tell you about in just a second. Of course, a singular one. So let's see. So let me just write down two varieties, one of which will be kind of easy to say what it is. And I'm doing it mostly for the purpose of saying what the second one is. So this is the kind of mirror dual. To P1 cross P1 in a precise sense. So there's toric mirror symmetry, which, so this is a toric variety, it's a two-dimensional toric variety, and which one is it? Well, so P1 cross P1 is, corresponds to this fan. So that's P1 cross P1. And the lattice matters, but so just, and this guy corresponds to the dual sitting inside the same lattice. What do I mean by dual? Well, there's a fairly simple duality theory of polytopes. So you think of this fan there's a diamond sitting in there, and then this is the fan over the faces of the diamond. So each cone is sort of generated by looking out over the face. And then if you take the polar dual polytope to that diamond, what you get is this square. Of course, it's also a diamond depending how you look on it, but the way it sits in the lattice now you take the fan over the faces of that square, and you get something that has singularities that kind of correspond to these extra little lattice points in there. So that's what X1 is. So this is the fan for it. So X2 is going to be P1 cross P1 cross P1, the same construction applied to that. So it's not quite so easy to write it down as a global quotient in this case, but this is, again, the mirror dual. And delta, so this is equal to x of delta. Delta is the fan over faces of a cube. The cube in R3. It's a very simple variety, somehow combinatorially speaking. Okay, I think we need that anymore. So Eric Katz and Sam Payne showed that for X1, so this is not surjective. So the restriction map is not surjective. And then they also showed that for X2, it's even less surjective. Even when you tensor with Q, it's less surjective. And so as a corollary, the equivariant K theory of X2 does not surject onto the non-equivariant K theory. And the proof is simple given everything that I've done, that I've said before. So you've got this map that you want to study, and one knows that this map exists. So this is x equals x2. And so there's a map to k hat, tensor with q, and this becomes isomorphic to a hat x tensor with q. So, and then the bottom row will just be forgetting the equivariant structure. So this is not surjective. It doesn't matter whether or not you complete in this particular case up here. Their theorem is degree by degree, so it will still remain not surjective. And it follows that this map is not surjective. But this map is surjective because X is a complete, well, it doesn't actually have to be complete, but it's a toric threefold. And one of the earlier results I mentioned said that this map was surjective. And well, right. So this map's surjective, this map's not surjective. That implies that this is not surjective. That's the proof. So yeah, I guess. So I can just say in words. So the way that Katz and Payne produce these examples is they develop enough computational tools on both sides to very, very explicitly compute this map. And the tool on this side is a device called an equivariant multiplicity, which is related to localization. And on this side, the analog is a Minkowski weight. So what we have in the K-theory setting, one could try to kind of ignore this whole Riemann-Roch and imitate their methods just here, and it should work. That we haven't finished doing that yet. What we do have is a theory of equivariant multiplicities in a localization type formula that lets you compute here. And we don't really know what the analog of Minkowski weights should be for toric varieties in K-theory. But sort of interesting.
Homotopy K-theory is also not surjective.
Yeah, but right, whatever equivariant homotopy K-theory may someday turn out to be. That's right. Yeah. So yeah, thanks for listening. That's all I have to say.
Questions?
Why is it easier to put these things in dimension 3?
So the question is why dimension 3? What's special about dimension 3? So